Hey everybody, I'm Bryan Meissner. This is Jeff Cardillo. We're going to talk to you about doing non-static or non-standard or really non-supported codecs with mostly standard WebRTC. All right, so first question is why would we do such a thing? So our use case was really focused around IoT cameras, so edge cameras doing really H.264 based on the encoder chip that was based on this thing. And so we were tied into the codec that we had because of these devices. We're looking to do ultra low latency, so we're talking sub-second latency so that we can facilitate two-way communications across these devices. So two-way communication, we want to be able to facilitate both audio and video, and we're tied into the codecs that these devices have. We've got massive scale, so we've got hundreds of thousands to millions of the devices out there that we're trying to support. So not only do we want to try and scale these things, but we want to try and reduce the cost of ownership and the cost of deploying these devices as well. So we want to see a parallelized workflow to facilitate really the one-to-one or one-to-a-couple type of workflows that these devices typically see. So WebRTC is great for these kind of workflows. It facilitates the latency, it facilitates the parallel workflow, and so we wanted to try and do this. Back when we did this originally, H.264 was not supported yet by the WebRTC libraries that were out there, and so we needed to do that. Or we needed to try and bake in support for H.264. Some of these devices also did AAC audio, which still isn't supported by the spec, as our last talker was mentioning, and so that's an issue as well. Looking forward, you'd be able to do some of this work for new codecs like AV1, or if you've got proprietary codecs that you wanted to be able to provide these kind of workflows for. Having said that, the WebRTC libraries now have gone through a bunch of re-architectures since we did this back in the day, and so they've got a much nicer codec factory than they had before. So if you've got the resources and the time to add a codec to that properly, we definitely recommend proper coding practices, but we don't always have the time to be able to do that, or we don't, there's other constraints, and so here we go. All right, so a little bit of background on WebRTC if anybody's not super familiar with it. WebRTC is a collection of protocols that first facilitate peering and connection identification across different peers. So it comes down to IPv6 or IPv4 IP discovery, trying to find peer routes through there through either direct IPv6 routing or UDP hole punching and NAT traversal. There's also a fallback for relay servers, but you try and keep that a small percentage of your actual workflow. And then once that peer channel is established, you set up then RTP and data channels to actually provide your actual media flows and kind of continue on your streaming from there. We didn't want to touch that media or the peering flow at all. We wanted to get all the goodness of WebRTC without having to modify that. And so really, by pushing our software down onto the actual edge devices, we were tied into the codecs that we had to use because of the hardware that we were running on, but we had full capability to modify the protocol and the packetization stacks from there. And so that's really what we did. We wanted to try and leverage the existing players that were out there. There was lots of players that could do H.264, and we wanted to be able to also maintain obviously the hardware encode on the camera side, but also hardware decode to keep the load light on the players downstream. So first thing we did was pick a protocol that was supported and just pretend to be that. And so at the time, really all we had was VP8 and G711, so we just masqueraded as that. We still took our H.264 and packed it into the normal RTP flow that it was expected that VP8 was going to come down. And so by doing that, the WebRTC stacks that were out there would be okay with us peering, and we'd get through the media flows. And really, we just needed to be careful about not sending H.264 into a VP8 encoder and blowing it up. And so that's what we did. So on Android, the first thing that we did was identify a player, and we chose an API-based player, which is Exo Player. Exo Player was great. It was well supported. It had hardware decode capabilities, and so we let the WebRTC stack come all the way into the point where we're dewrapping the RTP, And then once we were left with just really those raw H.264 frames, we could lift that out of the stack through a little bit of piping magic, drop it directly into the Exo Player APIs, and let Exo Player handle our decoding and rendering from there and totally bypassing the WebRTC decoder at that point. On iOS, we didn't have an API-based player, so we had to do it a little bit differently. So we looked around and found this is about the time that VLC came out with their hardware decode capabilities on iOS, and we thought that was pretty cool. And so we decided to go ahead and leverage that. We didn't want to modify VLC at all, but VLC's got a lot of really great ingest capabilities. And since we already had RTP coming in, we thought it'd be pretty cool to be able to trick it into thinking that we've got a local RTSP stream for it. And so we wrote a SDP file down to disk, telling it to go and look for RTP streams on a couple of local sockets. And then we would lift the RTP directly out of the WebRTC stack before the RTP got unwrapped, redirect it into those local sockets, and now VLC is just ingesting as if it was an external RTSP stream and handling the flow directly from there. So the VLC player would unwrap the RTP, decode, and render the frames directly, bypassing most of the flow of WebRTC at that point. Browsers were a little bit different. We couldn't go and modify the WebRTC stack because it's baked into the browser already. And we didn't want to introduce a big heavy plugin or do anything. We wanted to try and keep as native as possible, but we also still want to try and keep our latencies low enough to have two-way communication. So RTP wasn't an option for us because it was going to go down the media flow, and we couldn't send something non-supported down that media flow without modifying it. So we instead looked towards the data channel. This was pre-CMAF days, and so we kind of went through a couple of machinations on what we were going to send instead, and we aligned on fragmented MP4, and you can indeed send single frame fragments down a data channel, and so that's what we did. So we sent those single frame fragments down. WebRTC data channel's got a nice little hook so that in your web app you get just callbacks on each packet that arrives in on the data channel. So those frames would come in, we get notified on the web app on the JS side, and we can pipe it directly into media source extension. And the media source extension would handle the rendering through the video tag, and we were done. And so those were the different workarounds, and I'm going to toss it over to Jeff for the trade-offs that we saw.
Yeah, let's talk about some trade-offs. Can you guys hear me okay? All right, so let's take a quick step back and look at where we are, right? So we're using standard WebRTC peering to try to get two devices talking on pretty much any network topology, but we now have access to proprietary and non-standard encodings, which is great. We did run this in production for a number of years, so we know that it can work. However, there are some downsides to this, right? And complexity is a big one. So you may need to customize WebRTC for every platform you want to support. As you saw, we had a custom implementation for iOS, Android, and web. So you need really good control over your source. But another thing to keep in mind here is that you may lose access to other standard WebRTC features like synchronized audio and echo cancellation. Looking at some mobile trade-offs, more libraries means a bigger app, right? That's a given. But you may also have to bump your minimum SDK on Android, and this means leaving some customers behind if they're on older hardware. You will incur a very small amount of latency due to the different processing pipeline. And bug fixing becomes much harder now because you have to dig through more player code and custom WebRTC code to fix bugs. Keeping all of these pieces up to date can be a pain. And another thing to keep in mind is that both Exo Player and VLC tend to buffer on loss, and this can be another source of latency if it's not configured correctly. Let's see. Yep. And moving on to the browser and the data channel. So stream control transmission protocol wasn't meant for video-sized traffic, and because it guarantees packet delivery, it can cause bottlenecks on high latency connections. Not every browser supports data channels well. Edge and Safari were problematic. Edge will pick up data channel support as they move to Chromium. And finally, back when we did this, media source extension can be finicky when sending it frames directly. And so we did have to spend a lot of time massaging that flow in order to ensure a smooth and error-free experience. And that's it.